Alright, we finished 6C last time, which was construction of various tangent problems from simple, just here's a point on a circle, find the tangent to that point. Here's a point off of the circle, find the tangent from the point to the circle, two tangents rather. And some of those Apollonius's circle construction problems. So we'll move on. 6D is 3 hard problems, but I'm sort of going to match the next 2 sections together. So I'll just group these together now, and we'll talk about sort of both sections simultaneously. So 6D is 3 hard problems, and 6E is constructible numbers. I think I had said on Friday's class that I would push constructible numbers till Friday of this week, but then I assigned a homework problem that I thought if you know 6E, life is a whole lot easier. So we'll start here today. We'll start talking about sort of what numbers are constructible. And by a constructible number, I mean, of course, what do I mean by how do you construct a number? Well, I mean, can I find a length of a given number? Right, so can I construct a line segment of, say, you give me a number, and the question is, can I find a line segment of that given length? So we'll start with something easy. Do you think I can construct a length of 0? How would I construct 0? Just take a point, right? So let's say a number is constructible if we can construct a length let's say a number a. A number little a is constructible if we can construct a length or a line segment of length a. So 0, yeah, 0 is constructible, just construct a point. Then next up is, can I construct length 1? And the answer is, think about where we're going from here. How about other numbers like 2, 3, 4? What does 3 mean? Well, 3 really means just 3 times 1. Right? So once you establish a value for 1, then you've established the values for all the other numbers. So length 1 is really just establishing sort of my reference point, a unit. So just draw any length at all that you want. Draw any length and say, this is what I'm calling length 1. And that's sort of how 1 works. So 1, construct any line segment, any length, construct any segment AB and define its length to be what we'll forevermore call as length 1. Does that make sense? Right, you've got to establish your units before you can do anything else, whether you're working with inches or centimeters or miles. So you just draw any old segment and you say, all right, so this is the units I'm working with. This is what I'm going to call 1. All right, so 0 and 1 are constructible. Can I construct 2 based on this? How would I construct 2, Adam?
Erect the perpendicular to AB at either A or B, and then your compass remembers length, so you can draw a circle centered at, well, let's say you erect a perpendicular from B to AB, then take a circle of radius AB centered at B. Or, well, I guess you wouldn't even need that.
So yeah, I don't need the perpendicular at all, right? All I need to do is draw a circle and then extend the line.
Yeah.
Yeah.
Yeah, I was going to say erect a perpendicular to AB and then erect that perpendicular to that new line.
Yeah, I suppose you could do something like that, but even easier
Yeah,
is just draw circles, right? So 2, 3, 4, you can do them all the same way. Take your length 1, now draw a circle centered at this point. Oh, sorry, that's not centered at that point, that's going through that point. Draw a circle centered at this point, and then extend the line, and now I have length 2. And from there, hopefully you can see how to construct length 3, do the same thing. Come to your very last point, draw a circle centered at that point of radius 1. Now I have length 3. And so on. So once you've established a value for 1, or a length of 1, now you can do sort of all of the positive integers. I can construct 1, 2, 3, and so on. So now we have sort of all of z plus all of the positive integers. Is this construction totally clear for the integers? Because I haven't written down any details at all, it's just a simple drawing, but okay. From here, since you can construct all integers, and because we've talked about division, remember we did this construction, if I have a length and you tell me a value for n, I can divide that length into n equal slices. Now we can construct all the rationals, all the positive rationals. So using our construction for dividing a length into n equal segments, we can now construct all positive rationals. In fact, I'll be even clearer because we have 0 in here. We know we can do 0 as well. We can construct all non-negative rationals. Rationals, by the way, usually denoted by Q. Since I want to talk about only positive rationals, I'll put the plus. And then I really should. Maybe union with 0. Right, so for example, if I wanted to construct the rational number 7 over 5, all I would do is I would come in here, I would construct a length 7, and then we'd use our technique for dividing that into 5 equal slices. All right, so 1, 2, 3, 4. So we cut into 5 equal slices. Then this length here is 7/5. So this is kind of cool, right? It's, as long as you establish a length of 1, now you can give me any rational number that you want, and I can find a length of that number now. Can we do more? Well, remember what we did last time was kind of important, the geometric mean. Geometric mean was a square root of a product, right? And if I take one length to be 1, and then the other length to be a, then I can construct the geometric mean of those two lengths. And the geometric mean of a times 1 is the square root of a. Meaning I can construct any rational number, and then I can take its square root. So square roots are constructible too. So using our geometric mean construction, we can construct the geometric mean of a length A and let's just say, let's remove this singular stuff, we can construct the geometric mean of lengths A and 1 to construct the geometric mean of these two, which is the square root of A times 1, or just root A. Alright, so this goes even further. Now we can construct more than just rational numbers. We can construct square roots of rational numbers. Again, I always mean positive, of course, but hence we can construct square roots of constructible numbers. And notice I wrote that slightly differently than what I was saying out loud when I said we can construct square roots of rational numbers, but if a square root of a rational is constructible, now I can take the square root of a square root and get a fourth root. What else can we do? Well, it turns out that this is about it. But now we can start combining these things. What I mean by that is, if A is constructible and B is constructible, it's a set of constructible numbers closed under addition. Can I add them together and get a number that's still constructible? I hesitated there for a moment. I was wondering if I should use that language or not, but I believe everyone's taken 317. That's a prerequisite for this class. So you're comfortable with this idea of sets being closed under operations. That's part of being a vector space. I think a lot of people have taken 301. Abstract algebra. So yeah, the set of constructible numbers is closed under addition. We'll start listing these in order. Addition. Why is that? How do I add two constructible numbers together? Well, we had mentioned this in a proof last class. I believe it might have been the geometric mean proof or somewhere. But if I have one constructible length and I have another constructible length, how do I add them? Well, I can just use my compass memory to place this guy sort of end on end over here, right? So all I have to do is construct a length A, construct a length B, place them sort of linear, and there's A plus B. Okay, so under addition, can you see that using the exact same process I can easily subtract? Just place this length B here instead, and then I have A minus B. So under addition and subtraction. So here's A, here's B, and then here I have A minus B. But I can do more. When you work with numbers, what's the second most common operation you might think about? Multiplication. Can I multiply? And this is where I thought this would come in useful for one of the homework problems. So 3 is multiplication. And this one's not nearly as obvious as how to add or subtract. If I asked you right now to multiply two constructible numbers together and construct the length of their product, it would take you probably a little while. So here's the construction for multiplication. Draw length A. Where am I going to put this? Let's indicate that the whole thing is A. And come in here, and remember we always have our reference length of 1, so I can always come along here and say, okay, this is length 1 along here. And this is in the case where A is bigger than 1, but A might be less than 1, and 1 lives way out here, something like that. But if A is constructible, then I can always say, okay, here's length 1. And I want to multiply A by B, so I've got this other constructible number, that's length B. So position them like this, starting at the same point, but off by some angle. What I'm going to do, my 1 is in a bad spot here, I'm going to drop the line connecting B to 1. So maybe I should give the steps here. Steps. Draw lengths A and B. I won't be very precise with this, but draw lengths A and B as shown. Let's draw lengths A and B and 1 as shown. Step 2, oh boy. Sorry, I'm not happy about how to write these steps because now I want to talk about drawing this line, but I haven't labeled the vertices at all. And I don't really want to, but if you want to be very precise here, let's call that X, Y, Z, and W. Then now draw a line, WY, vertices labeled as shown again. And now we'll just extend this length B. So extend this length B. Extend this length B to a point V. And V is going to be such that when I drop VZ, it's parallel to WY. So extend the length B to a point V such that VZ is parallel to WY. And what I want you to do now is measure this length that we've constructed. That is some terrible brackets. So there's B, there's W. Measure that length. How are we going to do that? Well, let's give this length a name. How about we call this length C? How long is C? Well, what I have here is I have two similar triangles. Right, is it clear to you that they're similar? They share this angle. And because these two lines are parallel, this is a transversal. So these corresponding angles are equal as well. So by AA, those are similar triangles. So let's take ratios of sides. Here I have 1, this length 1 over B. So this side over this side should be in the same proportion as the two corresponding sides in the bigger triangle. It should be A over C. Hence, length C is indeed the product. And C is A times B. And that's the way people typically do multiplication with constructions. I looked in the textbook, but I couldn't find this anywhere in the textbook. At one point he references it and says we can multiply, but he never says how. Maybe I was missing it. But yeah, this is sort of the geometric construction of multiplication. And for a long time, by the way, before modern day algebra and arithmetic and everything came about, this is how people would do multiplication. If you wanted to multiply, you construct like this. It's crazy to think about. But using pretty much the exact same construction, we can divide. Or, I was giving them names. We were closed under addition, subtraction, and multiplication. So, and last but not least, and division. The construction is basically identical. Take your length A. So, length A. Mark off length 1 on it, and then take length B. Alright, well, drop that line, come in here, choose the point so that this is parallel. Doesn't look very parallel in my picture. If this whole thing is B, this is A, and I know I've constructed B must be the product of A times X, or I called it C before, then I must have A times C is B, so C is B over A. And now I've done division. I have constructed the length of B over A. What does this mean? We're closed under addition. We're closed under multiplication. We clearly have inverses and whatnot. If you've taken abstract algebra, the set of constructible numbers is a field under these two operations. So let's just say hence if A, let me just give you an example of the types of things we can construct. We're just going to build up a crazy number here. So I can construct 1. I can construct 3/11. I can construct the square root of 3/11, because I know I can take square roots. And I can add those together, because I can do addition. And because this is a constructible number, now I can square root that. That's still constructible. Then I could subtract off 5. Both of those are constructible numbers, so their difference is constructible. Then I could take the square root of that again. That's a constructible number. And I could divide by 4, and so on. All right, so this is getting pretty complex. The construction would take a while, but this is a constructible number. And it turns out that this really is all of them. All constructible numbers are built in this way. So you start off with 1. You essentially just start off with the number 1 and 0. And you take sums of length 1, or differences, or you can divide by other products of 1. You can take square roots. This is all of them. Again, in abstract algebra terms, what I'm doing is I'm taking all the positive rationals plus 0. I'm adjoining square roots, and then I'm taking field extensions of that, where I adjoin more square roots and square roots and square roots. So, turns out all constructible numbers are found, are built in this way. So I'm not being very precise here. I'm not writing down exactly what the set is. We're not going to prove it. But it turns out this is how you build all constructible numbers. So in comes these 3 ancient, the textbook calls them hard problems. They're really impossible problems. But these three hard problems that these ancient Greek mathematicians were looking at, and they weren't solved until modern day means, where they were proven to be impossible. And the solution to proving that they were impossible was really studying what numbers are constructible and what numbers aren't. For example, do you think I'd ever be able to get a cube root this way? I can get 4th roots by taking square root of a square root. So I can get all these even powers. But yeah, just doing this, I can never get cube roots. And if you prove, for example, that the cube root of 2 is inconstructible, then that knocks out one of these very hard or impossible constructions. So this is the classic hard problem, number 1. And this is doubling a cube. So before we get to doubling a cube, let's talk about how this relates to our homework. So here's also a classic problem, but not one of these impossible ones. Double a given square. What do I mean by this? What do I mean by double a square? I mean, given a square, I want to construct another square whose area is twice the original. All right, so this is what people mean by double a square or double a cube. Construct a square with twice the area of the original. So your homework problem is more complicated than this. I think it's 6C.3 or something. It's find a square that has n times the area of the original. Here this is just 2, so this is the n equals 2 case. And the solution, actually lots of ways you can do this, but the typical solution, the classical solution, is to use Pythagoras. So solution, let's just sketch it. It's obvious enough that we'll just sketch it. I have a square. This is what we start with. Side lengths, let's call them S. to construct a square with twice the area, how long of a length do I need to construct? What should the length of the bigger square be? Well, the original area is s squared, right? So if I want 2 times the area, I want to construct an area of 2s squared. So,
√2.
So s would be, so we want sides of length √2s. How do I get √2s from this picture? Well, Pythagoras, right? Drawing this diagonal, that's a right triangle. And the length of the hypotenuse is the square root of s squared plus s squared, square root of 2s squared. This is length square root of 2s. And then there's nothing fancy to do here. Once we have a length, we've already talked about how to build a square of a given length. So once you have a length, erect your perpendiculars and so on. So just draw on this square. So I didn't write down his steps or anything, but that construction should be clear enough, I think. Any questions with that? So there's the classic construction. There's other ways you can do this. You don't even have to invoke Pythagoras. You can just, for example, take this triangle when you divide, and then you can think about making copies of it. Make 4 copies of it, and you can show that the 4 copies of it have twice the area of the original square. Things like that. And you can prove that 4 copies arranged in this way must be a square, and so on. So there's lots of different ways to prove this. But the question for homework is not double a square, construct n times the area of a square. And this technique just doesn't work for n in general. You could do other things like you could say, okay, I have my square of length s, and then I could make 3 copies of my square. So this is 3s, and then you could take that hypotenuse. But how long is that hypotenuse now? This would be 9s squared plus s squared. This would be √10s. I don't know why I went straight to 3. I should have done 2. So that would be √10s. If you take 2 copies, what would that be? That would be √5s. But using this type of idea, I can't find any way to sort of get like √3. Alright, so there you're skipping numbers. So here comes in the homework problem 16.3. N times the area is the problem. And I would get away from this sort of construction that we're doing entirely. Remember, all I really wanted to do was construct √2 times s, right? For n times the area, what do I want to construct? I want to construct √n times s. That's what I'm looking for. And another way to get root 2 times s without doing Pythagoras and all that stuff is just, I have a length s. Root 2 is a constructible number, so I can construct a length of root 2. Agreed? And then I can do products. So I can construct a length of, I can come into s and I can multiply. I can multiply and say, okay, there's root 2 times s. Because I know I can multiply. And root 2 is constructible. I don't know why my handwriting has gotten so terrible all of a sudden, but maybe that's always as bad. So you can do the exact same with this, right? If you want to do n times the area, I just want to construct this. Construct root n, take your length s, multiply it by root n, and then build the square. So in these terms, it's actually not a very hard problem at all. That's all of it. Now just write down the details. And again, you don't need to provide all the intermediate steps, right? When I say construct root n times s, you can just say, because we know we can multiply, construct it, right? Don't write the details for how to construct it. But there's doubling a square. The classic problem from antiquity is double a cube. So you're given a cube, construct a cube with volume twice the original. Double a given cube. And obviously we can't construct cubes, right? So this isn't exactly what I mean. I can't construct three-dimensional figures on a piece of paper with a compass and a straight edge, but in the problem of doubling a square, what it really amounts to is if I'm given a length s, can I construct another length, which is one of the sides of the square, so that when I build the square, that has volume, or area twice the original. Same thing is happening here. When I say double a cube, I mean I'm given one edge length of the cube. Can I construct the edge length of a cube with twice the volume? All right, so i.e. given an edge of the cube, or of a cube, construct an edge of the cube with twice the volume. So we're not actually constructing this three-dimensional figure, it's just an edge. All right, so once again, just if I have an s, can I find from here a length that would be an edge of the cube with twice the volume? Well, so our original length, if our original length is s, then our original volume what's the volume going to be? S cubed. So twice the volume is 2s cubed. So our new length for twice the volume, we want cube root of 2s. So the question is really, can we construct root 2, or sorry, cube root of 2 times s? Well, if I could, S is a constructible number, because I start with S. Or in other words, if I'm starting with it, I'm really calling it length 1, or you can think of dividing by S. In any case, really, this is all I care about. If I could construct this, then I could construct cube root 2. And for literally thousands of years, people dwelled on this. And it was believed to be, at least the ancient Greeks believed this to be just a very difficult problem. They didn't sort of conceive that it was possible, just that it was hard. If we keep looking, we'll find a solution. But you can prove that this number is not constructible through modern algebraic techniques. I believe Carl Gauss originally did it in the late 1700s, early 1800s, so very recent times. You can show this is not constructible. No. So this is coming about in the early 1800s. But finally, with modern algebraic techniques, you can show this isn't a possible construction. It just can't be done. No matter how much you try with a compass and straight edge, you will never be able to double a cube. So this construction is not possible. Still to this day, because these problems are so easy to state, because understanding compass and straight edge constructions are fairly easy, you still get people out there that keep trying to solve these things. They keep coming up with solutions, but they're breaking their rules all the time. And I think when people say this is impossible, they misunderstand what impossible means. It's not just it's a hard problem that no one's been able to solve yet. It's literally provably impossible to do. If you break the rules a little bit, for example, if you have your straight edge and you put a marking on it, so you turn it into a ruler essentially, now you can do things like this. So we have two more classic problems to talk about. Squaring a circle. So if I have a circle, can I find a square with the same area? Provably impossible. And trisecting an angle. So instead of bisecting it in half, can I cut it into 3 equal angles? And for some angles it's possible. For example, a 90-degree angle is no problem. But you can't do it for arbitrary angles. And we'll prove, or we won't prove it, but it's notably impossible to do for a 60-degree angle. So, and 60 degrees, remember we can construct 60 degrees. Just take an equilateral triangle. Here's a 60-degree triangle, or a 60-degree angle. You provably cannot trisect that. So that's the 3 classic problems, and then there's one more. Not one of these 3 classic impossible problems, but still a classic problem in a sense. What regular polygons can we construct? Right, we know we can construct regular triangles, that's the equilateral triangle. We can construct squares. Constructing a regular pentagon is harder, but the ancient Greeks knew how to do this. And that was about it. They could construct 3, 4, and 5 gons, and then it's easy to double those numbers. So you can double 3 to get 6, you can double 4 to get 8, you can double 5 to get 10, and so on. But what else can you do? For example, they couldn't find a construction of a regular 7-gon, a regular heptagon. And it turns out it's impossible. So in comes Carl Gauss again. Carl Gauss proves he can construct a 17-gon. He does this when he's 18 years old in the late 1700s, which is impressive because, for almost 2,000 years, in fact, probably 2,000 years, no one had been able to do that. But we'll talk about all that next time, I guess. And we'll end here.